Okay, so now we understand that how we can change the amount of light that is falling. It's through lenses and this aperture opening. And once it falls on these sensors, we know what an image is over there. Now, I talked about the current flowing once these light rays are falling on these sensors, right? Now, based on that, the amount of current that's flowing in each of those pixels, the computer actually measures what is the amount of current that's flowing. So we can do that very precisely. And because it knows the amount of current, we can associate a number corresponding to a pixel. So, for example, at a particular pixel, we can say that red is 235, green is 245, blue is 205. So this essentially means that so here we are basically, let's say if the maximum current was a certain number and the minimum current was certain number, then we will rescale this. But what do I mean by rescaling? So the minimum amount of current is, I will say, is zero. So I will associate a number with it. I'll say zero. And the maximum amount of current is, let's say, 1 ampere. I will say it is 255. Okay. So at each pixel, I can say the red is between 0 and 255. Similarly, green is between 0 and 255. Blue is between 0 and 255. So the more the current is, the more it would be closer to 255. And the lesser the current is flowing, it would correspond to zero, closer to being zero. So basically, like when we're looking at an image, for us, it's we can perceive colors, right? We can say it's red, green, blue, pink, whatever. But for computers, there's there's no notion of colors for them, right? For computers, it's just numbers. They just deal with these binary. They just deal with uh, numbers. So based on the current that's flowing, they just know that at a certain point, red is, let's say, 240, green is 255, blue is blue is 110. So this corresponds to different amounts of color currents flowing for different sensors for each pixel. Now, can anybody tell me what would be the color that would be perceived by the humans at a pixel when red, green, and blue, all three are maximum? Let's say 255.
White.
Yeah, that's correct. That's a great answer. And this would be because, as we talked, if we mix red, green, and blue complete at full intensities, it produces the color white. Okay. And what if it's 0, 0, and 0? Red, green, blue, all three are 0.
Black.
That's correct. Because then there would be no red, no blue, no green. So there's no color. So this is what computers are seeing. So we see this beautiful image, right? But if you see, if I zoom in a small patch, as it's shown, the computer is only seeing these numbers for red, green, and blue all. Now these numbers can be integers or they can be floating. These can be like decimals as well. We can use them in both representations. Now you understand that these are numbers, right? Corresponding to different colors. Now, first of all, did everyone understand why why it was white or why it was black? The examples that I gave. Is there anyone who wants to ask? By the way, I see there's been an interesting discussion that's going on in the chat. Yeah, I didn't see that was convex lens. Yeah, sorry about that. And uh, Yeah, for exactly. Aditi mentioned that photons and electrons is a different area that's worth looking up. So everything, so computers that you're seeing, all the functioning of the computers, that's been possible only because of all the advances that have been in physics. With we can control the we can measure we can measure precisely the amount of electricity that's flowing in these sensors, and that's like years of research that has come to this. And yeah, so like there are digital sensors, there are cones and rods that detect different colors and the intensity of light in our eyes. uh, yeah okay, so now we understand what different values, what different currents flowing correspond to, and now you see these faces, right? So you, for humans it's very easy to perceive that these are all the same faces, right? But if you think about what the computer is seeing, so computer is essentially seeing numbers, right? So if I see, let's say, the forehead. Now the forehead in the first image is pretty dark because there's not enough light falling on it, and on the rightmost image the forehead is very bright. Now, for us, it's still the same face because the structure is the same. But for computers, if you see at the forehead, so here the value would be closer to 255 because it seems like a lot of colors are present. But in the leftmost image, the numbers would be closer to zero. So the computer sees so much difference, right? It sees from 0 to 255 at forehead, but so how is it supposed to identify that it's the same person because the values are changing so much? So this is what I'm talking about. So in these image matrices that computer is seeing, these numbers that the computer is seeing, it's not just about numbers at each single value that have to match. So if it's the same image, so if I tell a computer that the rightmost, that this person is person A by giving it the rightmost image, now if I give it the same image, it would know that it's the same numbers and it would say it's the same person. But if I give it, let's say, the leftmost image, and if I ask it just to match these numbers, then it's going to say that it's a different person because it would say that the values are completely different. But we know that the values are different only because of the illumination. And what's important to capture is the structure, it's the local structure. So there's a certain ratio between, let's say, the different parts of this person's face, so the distance between eyes, the distance between nose and the mouth, and so on. So it's the structure that counts, and that's what we want to imbibe. That's the information that we want to imbibe in the computer vision algorithms. That's what we're moving towards. That's how science started around understanding images. Then there are other problems, these such as occlusion. So if you see this image, you understand, okay, so there are trees that might be blocking this person. There are some trees that block this person, some trees do not. But how computer vision algorithms supposed to understand what objects are in the front and what objects are in the back? Because it's just seeing a 2D image. The image from the horse would not come to the lens if there's a tree in front of it. But how is the computer supposed to understand what's in the front, what's in the back? So these are some, I'm talking about some challenges that are there to understand this random rectangle of numbers. Again, let's say, for example, you want to identify a chairs in an image, right? But then there are chairs of so many types. How can a computer identify all these different kinds of chairs? And for example, let's say if I keep a stack of books, now as humans you understand that you can sit on it, but how is computer vision algorithm supposed to understand that you can sit on a chair, and even though they are books, you can still sit on them? So it's called understanding affordances in computer vision research. So how are you able to understand what scene means? And then colors, so colors are again perceived by different people differently. So even though at each of these pixels there are some numbers, such as there would be some value for red, something for green, something for blue, but for computers, so all these values are the same, but humans perceive it differently. So can you guys unmute and tell me what colors you see here? So how many of you see blue and black, let's say?
I am seeing a mixture of white and golden type shade, brown,
Same.
golden.
Yeah, so you're seeing white and golden, but I'm
Yes,
sure there would be a lot of people. So, for example, I'm not seeing white and golden. For me, it's blue and black. So, is there anybody who's also seeing blue and black?
Yes, sir. I can.
Yes, and it seems pretty crazy to think that it's, yeah. So there's another color, yellow and pinkish white. Now, for other people, it's impossible to think that it's blue or black. For some people, it's impossible to think it's yellow and pinkish, right? And that is because the sensors in our eyes, the thing that Aditi was talking about, the rods and cones, they have they are different in different people, right? And that's why this is being perceived differently by each of us. Yeah, so somebody says it's blue and golden. So that's what I'm talking about. We all have different sensors, so we have different perceptions. And also there are some disabilities related to these sensors in our eyes, such as color blindness. So So if humans are perceiving colors differently, what is a computer supposed to perceive? Is there a single answer to it? So these are the kind of questions that we want to answer here. I'm sure you must have found this fascinating. If you want to look up further on source and all, so this is, you can search for the dress. I think it's that's the search term. And then there's motion. So we all understand what this bird is doing in this, right? It's rotating its head really fast. But how is a computer supposed to understand the rest of the body is static and it's moving its head really fast? What is the motion of the head? So we understand it's a circular motion, it's rotating by about its neck. But what is a computer supposed to understand from this? It's a pretty random image for a computer because it's seeing these pixels and it has never seen them before.
So I think the computer will think that the bird that is like this only.
Yeah, exactly. So if I give it a lot of images and say that these are all birds, then it would think this is what a bird looks like, and it would never understand that it has a beak. That's correct. Now there are some things that change when we capture an image, right? So for example, if you see a rail track, so in a rail track, what happens is, oops, I stopped sharing accidentally. You can see again, right? So a rail track is parallel, right? But in an image, if you see, these are intersecting, right? Now how does that make sense? uh, so that's what happens that's what happens uh, when this 3D world forms an image. Then often some of the things are not preserved. For example, the rail tracks that are actually parallel, you know it as a fact, but in a 2D image it's not parallel. So how is a computer supposed to understand what's parallel in this image, for example? Now those of you who are artists, you would know that when you're drawing something, some perspective, you need to think in terms of what would be parallel, what would not be parallel, which lines would look like what in a painting. So that's why when you draw a scenery, for example, if you try to paint a river, for example, then you understand what would be the ratio, how it would be changing as the river is coming nearer to the camera, let's say. So these are the tools that help us along the way to do computer vision. We lots of math, programming, understanding of how light is reflected and images are formed. So physics also. There are tons of other fields that